Hello children, welcome to our physics class. Hope you all are fine over there. In the previous session we discussed moment of inertia. Also we discussed moment of inertia of different shapes. Today we are going to discuss the kinematics and dynamics of rotational motion about a fixed axis. So many concepts are included under this title, Kinematics of Rotational Motion and Dynamics of Rotational Motion. So let's discuss about all those concepts today. First, in the kinematics of rotational motion about a fixed axis, we are discussing about the equations of motion. You all are familiar with the Newton's equations of motion. You had studied like this: V is equal to U plus AT, S is equal to UT plus half AT square, and V square is equal to U square plus 2AS. So here instead of U they have given V0. That's the only difference. Okay, and instead of S, that is displacement, they have given X here and they have given X0 here. Okay, so X minus X0, if we take X0 to the LHS part, you will get X minus X0, and X minus X0 is equal to displacement S. So this equation represents the second equation of motion. S is equal to UT plus half AT square, where U is replaced by V0. Okay, so V square is equal to V0 square plus 2AX. So instead of X you can take S here. Okay, anyway, these are the equations of motion in the translational motion or linear motion, and the analog of these equations of motion in rotational case will look like this. So instead of linear velocity V, here we can write the angular velocity omega. V naught is replaced by omega naught plus AT, and here acceleration A, linear acceleration A, is replaced by angular acceleration alpha. So the equation will become omega equal to omega naught plus alpha t. And here X is equal to X naught plus V naught t plus half AT square. So it is replaced by theta equal to theta naught plus omega naught t plus half alpha t square, where theta and theta naught are the displacements, angular displacements. Okay, now V square equal to V0 square plus 2AX. Here in the rotational case it is replaced by omega square equal to omega naught square plus 2 alpha. A is replaced by alpha into theta minus theta 0, because X is, instead of X we can consider S here. Okay, here S is replaced by S. Actually the equation of motion is V square is equal to U square plus 2AS, isn't it? So here instead of U they have written V0 plus 2AS, and we know S is nothing but the change in position, that is S is X minus X naught, and in the rotational case it will become omega square is equal to omega naught square plus 2 alpha into theta minus theta naught, that is the angular displacement. Okay, but theta is the angular displacement after a time t, and theta 0 is the initial angular displacement of the rotating body. Theta and theta 0 are marked here. Consider the points P on a rotating body. So as the body rotates, the point P also moves. So initially this was the position of point P, and this is the initially this is the position, and initially the object has displaced by a certain angle theta 0. So this is the initial displacement, and as time goes on the point P reaches here. So this will be the angular displacement for this position. Okay, so theta 0 is the initial angular displacement, and theta is the angular displacement after a time t. Next, we can discuss the kinetic energy of a rigid body, especially kinetic energy of a rotating rigid body. We know the kinetic energy for an object in linear motion is half mv square. So what about the kinetic energy of an object which executes a rotational motion? It is not half mv square, but it is something else. So let's try to find out the expression for kinetic energy of a rotating body. So for that, consider a rigid body as shown on the figure. This is a rigid body, and inside the rigid body many particles are there. We are considering 3 such particles for our convenience. Let the first particle be of mass m1, and it is situated at a distance of r1 from the axis, from the center of this axis, that is O, and v1 is the direction of linear velocity of that particle. Whenever the particle executes a rotational motion, the particles inside the rotating body executes a linear motion also along with the rotational motion. So v1 be the linear, the direction of linear velocity is given by v1. Then let another particle m2 be situated at a distance of r2 from the point O. Then v2 is the linear velocity of that particle. Another particle m3, it is situated at a distance of r3 from the point O. v3 is the linear velocity of that particle. So let's try to find out the expression for first kinetic energy for first particle. So the kinetic energy of first particle of mass m1, so let it be k1. Kinetic energy of first particle is, you know, the kinetic energy equation is half mv square. For the first particle we can write it as half m1 v1 square equal to half m1. We have already studied one expression that v is equal to r omega. So v1 is equal to r1 omega. v1 square will be equal to r1 square omega square. Similarly, kinetic energy of the second particle is half m2 v2 square equal to half m2 r2 square omega square, and kinetic energy of the third particle is half m3 v3 square equal to half m3 r3 square omega square. No need to write omega 1, omega 2, omega 3 like that, because the body is rotating with the same angular velocity omega. So inside the body all the particles also rotate with the same angular velocity omega. The angular velocity does not change with the particles. Okay, then what will be the total kinetic energy of the rigid body? Total kinetic energy of the rigid body will be equal to sum of kinetic energy of all the particles. So here total kinetic energy will be k1 plus k2 plus k3, like that. So we can write the total kinetic energy will be half. Also omega square is a constant factor. Omega square into m1 r1 square plus m2 r2 square plus m3 r3 square. Okay, now m3 r3 square. Now what is this m1 r1 square, m2 r2 square, m3 r3 square? m1 r1 square is the moment of inertia of the first particle. m2 r2 square is moment of inertia of the second particle. m3 r3 square is moment of inertia of the third particle. So the sum of m1 r1 square, m2 r2 square and m3 r3 square will be total moment of inertia of the rigid body, and the moment of inertia of the rigid body is denoted by I. So kinetic energy K is equal to half omega square into I, because the terms inside the bracket represents the total moment of inertia of the rigid body. So we will get the expression for kinetic energy K is equal to half I omega square. This is the expression for kinetic energy of a rotating rigid body. So half mv square is the kinetic energy equation for linear motion. Half I omega square is the kinetic energy expression for a rotational motion. Okay.